Hi, this is Luke from the Stats Medic, and in this video we're going to talk about binomial distributions, specifically the 10% and the large counts conditions. And the activity that we're going to use for this is called Do You Like Green Skittles? So there are two learning targets for today. The first one is to check the 10% condition to be able to assume independence of observations. And the second learning target is to check the large counts condition to use the normal approximation to the binomial distribution. Now, for this lesson, you are going to have to use a whole lot of previous knowledge that we've come up with over the last couple of days about binomial distributions. So I'd like to specifically remind you of everything that we know at this point. So the first thing is that we know how to check that a given scenario is a binomial distribution by checking the four conditions that we remember using the acronym BINS. So let me remind you what each one of those stands for. B stands for binary, which means that each trial is either a success or a failure. I stands for independent, which means that the outcome of one trial is independent of the outcome of another trial. N says that the number of trials is fixed. And we usually use the lowercase letter n to represent the fixed number of trials. And then S says that there is the same probability of success for each trial, and typically we'll use lowercase p to represent that probability. Now, the other thing that we know is how to calculate probabilities for binomial distributions. Specifically, if we want to find the probability of exactly k successes out of the n trials. And we have a binomial formula for that, which says n choose k times the probability of success raised to the number of successes times the probability of failure raised to the number of failures. Now, we also know about a couple of calculator functions that are helpful in this context. Instead of using that binomial formula that we have there, if you want to find the probability that x is exactly equal to k, the calculator function binomial PDF will allow you to do that. And the inputs or the arguments for the calculator on that one are n, p, k. Now we have another calculator function that will allow us to find the probability that x is less than or equal to k, and that is the binomial CDF function, and it has the same inputs, n, p, k. Now, two other things that we're going to need for today's lesson. For a binomial distribution, we have formulas for calculating the mean of the binomial distribution and the standard deviation of the binomial distribution. The mean is given by n times p, and the standard deviation is given by the square root of n times p times 1 minus p. Now, one final note that will be important for today's lesson. Remember, we talked about the distinction between sampling with or without replacement, and that when we sample without replacement, that means that the probability of each trial changes just slightly from one trial to the next because we're removing an item from the population. Now let's take a look at the activity. So this activity is titled, Do You Like Green Skittles? So let's see what it says. In 2013, Skittles changed the flavor of green from lime to sour apple, which in my opinion was a huge mistake. Mr. Wilcox takes a small handful of 5 Skittles from a bin of 10,000 Skittles and gets all green, which of course is terrible. Now, if 20% of the Skittles are green, what is the probability of this happening? So I'd like you to go through and try questions 1 through 4, but I'd like you to pause after question number 4. So if you could put a little marker in the margin here with a note to yourself to stop, I'd like you to go ahead and pause the video, work through 1 through 4, and then come back to check your answers before you move on to question number 5. So go ahead and pause the video now. So let's go ahead and check in with your answers for questions 1 through 4. Now, I am going to ask that during the debrief that you use a pen or a marker that is a different color than the pen or marker that you used for your original work. So leave everything that you have written, but anything that you want to add on would be in a different color. So for me, I'm going to use red to write on top of the answers here. So let's look at question number 1. Is this a binomial setting? And we already know how to check that using the BINS acronym. So let's just go through one by one. For B, we have binary, and definitely each observation is a success, which we've defined as green, or a failure, which is defined as not green. Quick reminder here that a success does not always mean that something awesome happened, like in this case when you get a green Skittle. Now let's check I, the independent condition, and here is where we have a problem. And the reason that we don't have independence of trials is because we are sampling without replacement. So when we take that handful of 5 Skittles all at once, that is equivalent to sampling without replacement, because a single Skittle cannot be selected twice. So this is our big issue, and therefore the binomial setting is not satisfied because the independent condition is not satisfied. Even though we do have the last 2 conditions, the number of observations is fixed, n equals 5, and there would be the same probability of success if we had been sampling with replacement. So out of number 1, we get the idea that this is not in fact, technically not in fact, a binomial setting. So number 2, we want to find the probability of getting the 5 green Skittles, given that this is not a binomial setting, which means we have to go back to what we know about probability. And that is the probability of these 5 events happening can be found by just multiplying the probability of each event. And so the first event would be that the first Skittle is green, and there's 2,000 out of the 10,000. But remember, we're sampling without replacement, so that first green Skittle has now been removed from the bin, which means the probability that the second Skittle is green is now 1 less on the top and 1 less on the bottom, 1999 over 9999. And then we're going to have to continue to take out single green Skittles as we move through. Third green Skittle, fourth, and fifth. We multiply all those probabilities, and we get 0.000319. Now, number 3 says find the probability of getting 5 green Skittles if this were a binomial setting. Okay, if this was a binomial setting, we know how to find the probability that x is exactly equal to 5 by using the formula. The probability that x equals k is n choose k times the probability of success to the number of successes, probability of failure raised to the number of failures, which ends up being 0.000320. So number 4, here's the important question. How do your answers from number 2 and number 3 compare? Well, number 2, number 3, almost exactly the same answer there, right? So we said almost the same. And when we think about why this is, it's because as we go through and we take out 1 green Skittle, there's 10,000 Skittles here total. So that's not really changing this probability that each Skittle is green by very much. So we said that the probabilities in number 2 change so little because the sample size is small relative to the population size. Now that's very easy to see here because we're only taking 5 Skittles out of 10,000. But we need to have some sort of general rule about what is a small sample size relative to the population size. And we do have an answer for that, and it's what's called the 10% condition. So let's make sure that you add this out into the margin here. And the 10% condition says that the sample size is small relative to the population. And specifically, we want the sample size to be less than or equal to 10% of the population. And here's how I'm going to write it. Lowercase n, less than or equal to. Now 10% I'm going to write as 1/10, and I'm going to use capital N to represent the population size. So this lowercase n, we're used to this one, that represents the sample size, and we want it to be less than or equal to 1/10 of capital N, which is our population size. Now definitely in this case, our 5 Skittles out of the 10,000 is less than 10%. And what that means is we can sort of relax this issue that we had here about independence, and for the most part we can assume that each trial is independent from the next, because that sample size is so small relative to the population. So now that we've checked in on the first half of the activity, I'd like you to now try the second half of the activity all the way down to the bottom of the page here. So you're going to work through the rest of your activity. So go ahead and pause the video now. So let's check in with your answers for 5 through 8. So the scenario is a little bit different here because Mr. Wilcox now grabs a huge handful of 100 Skittles from the large bin of 10,000 Skittles. Let x equal the number of green Skittles in a handful of 100 Skittles. X can be considered a binomial random variable because the 10% condition is satisfied, right? 100 is definitely less than 10% of 10,000. So number 5, what's the probability of getting at most 11 green Skittles? Show your work. Now in this picture here, at most 11 green Skittles, I can see here's 11, here's 10, 9, 8. So we're trying to add up all of those bars in that little histogram that you see there. And we know that we can use a calculator function to do that. And because we want less than or equal to some value, we're going to use binomial CDF rather than PDF. Now, very important here is that you must label the inputs, the calculator inputs. The 100 is the sample size n. The probability of success p is 0.20, and then k is 11. And we get an answer of 0.0126. So there's only about a 1.3% chance that we would get 11 or less green Skittles out of this sample of 100. Now number 6, the approximate shape of the distribution. Well, I sure hope that you look at this distribution over here and you see something that looks approximately normal. So I'm going to put a capital N on that to say that it looks like it's approximately normal. Now number 7, calculate the mean and the standard deviation. Well, we have some formulas that we know here. For the mean of a binomial distribution is n times p, and the standard deviation of a binomial distribution is square root of n times p times 1 minus p. Very easy to calculate the mean there as 20, as expected by looking at the picture of the distribution, and a standard deviation of 4. So I'm going to go ahead and add that to my picture, a mean of 20 and a standard deviation of 4. So now number 8 says redo problem number 5 using a normal distribution. Well, in problem number 5, we found the probability of getting 11 or less green Skittles. Well, we could definitely just use a normal distribution and find the area of that red shaded region there. And we've done lots and lots of practice with finding area under a normal distribution. We do that by finding a z-score, which tells me here that it is 2.25 standard deviations below the mean. And then, of course, to go from here to here, we'd have to look up that area in table A, and we get an answer of 0.0122. Now, hopefully, you recognize that your answer using the normal distribution is almost exactly the same as the answer you got using a binomial distribution. And that seems to make sense because in this picture, it is very clear that we have something that looks approximately normal. But we need to have some sort of general rule about when we can safely approximate a binomial distribution with a normal distribution. So in order to help us figure out whether or not a normal approximation is appropriate, let's take a look at an applet. So this applet will allow us to see if the normal distribution is a good approximation for the binomial distribution. So I'm going to start with the data from the activity where Mr. Wilcox took a random sample of 100 Skittles, and each one of those Skittles had a 20% chance of being a green Skittle. Now, we had already decided in the activity that this binomial distribution looked approximately normal, and we can see that in the picture here where the binomial distribution is represented as these yellow bars here, and then superimposed on top of that is this red normal distribution curve that in this case looks almost exactly the same as those yellow bars. So in this case, it's safe to use a normal approximation to the binomial distribution. But what happens if we start to change the number of trials n and the probability of success p? Well, let's start by changing the number of trials n. So watch what happens as I decrease the number of trials. And I'll go down to the extreme low end, say number of trials 8 here. And here's what you'll notice. The binomial distribution represented by the yellow bars is not really being approximated quite well with this red normal curve here. So the first thing to realize is that as we increase the number of trials, that normal approximation to the binomial becomes better and better. But now let's investigate what happens if we change the probability of success. So in order to do that, let me start with a number of trials of, say, 30. And I'm going to go ahead and change the probability of success. So watch what happens as I start to increase the probability of success. So here we're at about 50%. And I'm going to go all the way to the extreme end on the right with a probability of success of 0.93. Now, if you look at the yellow bars of the binomial distribution here, you can see that they are clearly skewed to the left, which means the normal approximation is not going to be a good approximation here. Now, similarly, if I take the probability of success to the extreme low end, you're going to see a similar phenomenon here, where the binomial distribution represented by the yellow bars is now skewed to the right, which means that the normal approximation is not going to be a good one here. Now, when the probability of success is somewhere towards the middle, you're going to see that the normal approximation seems to be much better than it did on the extreme ends here. So overall, what we're finding is that the probability of success that's very, very low or very, very high is not very good for using the normal approximation, but somewhere in the middle works quite well. So we're going to have to combine those two ideas together into what we call the large counts condition. And the large counts condition says that if we take n times p, it has to be greater than or equal to 10. And then n times 1 minus p has to be greater than or equal to 10. So in this case, n, 30, times p of 0.5 will give you 15. Well, 15 is the expected number of successes here, which is greater than or equal to 10. And with 15 expected successes, that means that we also have 15 expected failures here, which is also greater than or equal to 10, which means for n equals 30 and p equals 0.5, we are safe to use a normal approximation to the binomial distribution. So from the applet, we've come up with what's called the large counts condition. So let's go ahead and record this here. So for the large counts condition, what we decided was that n times p has to be greater than or equal to 10, and n times 1 minus p has to be greater than or equal to 10. And remember that this n times p is really just the number of successes, and this n times 1 minus p is really the number of failures. So we need the number of successes and the number of failures to both be greater than or equal to 10, which would allow us then to use the normal approximation to the binomial distribution. So let's see if we can summarize our learning in the important ideas on the next page. So let's go back to the two learning targets from the beginning of the lesson. The first learning target was about the 10% condition. And what we discovered in the activity was that we have to check the 10% condition anytime we are sampling without replacement. So we'll say here, when sampling without replacement, we can assume independence of trials which would then allow us to use a binomial distribution if lowercase n is less than or equal to 1/10 capital N, where lowercase n is the sample size and capital N is the population size. Okay, learning target number 2 was about the large counts condition. And we're going to check the large counts condition if we want to use a normal approximation to the binomial distribution. So we'll say we can use a normal approximation for a binomial distribution, if, and there's two things that have to be true here, n times p greater than or equal to 10, and n times 1 minus p greater than or equal to 10. Remembering that this n times p is really the number of successes, and this n times 1 minus p is the number of failures. So now that we have our important ideas, let's see if you can apply that learning in a new context by going through the Check Your Understanding. So you've got 4 questions to work through here, and then you'll come back to check your answers. So go ahead and pause the video now. Let's see how you did on the Check Your Understanding. So in question number 1, we were asked to explain why we can use a binomial distribution in this context. And so of course we want to check our 4 conditions for a binomial distribution by using the acronym BINS. And for binary, we know that each trial is a success or failure, and we've clearly defined the success as eating breakfast for a student and failure as no breakfast. The independent condition is where we're a little bit worried here because there is no replacement. We're not selecting the students and then putting them back into the pool. And so technically here, each trial is not independent because of the fact that we're not replacing. But this is where we can use the 10% condition. And so we check that the sample size of 500 is less than 10% of the total population, in this case, all high school students, which is definitely going to be true. So because of the 10% condition here, we can say that the independent condition is satisfied. And then we check number of trials is fixed. That's true at n equals 500, and we do have the same probability of success for each trial of 65%. So in question 2, now that we know that it's binomial, or that we can safely assume that it's binomial, we can calculate the probability of 300 or fewer high school students. This is definitely one where you're going to use the calculator to help you, and it is a situation where you need binomial CDF rather than PDF, because we are finding the probability of less than or equal to a given value of 300. And we end up with a final answer of about 1% there, 0.0113. Now question 3 asks if we can model the distribution of x using a normal distribution. And this is where we want to check n times p and n times 1 minus p, both greater than or equal to 10. Of course, this is the large counts condition. And we are definitely very safe here because our expected number of successes is 325 and the expected number of failures is 175, both very clearly greater than or equal to 10. So this means we can use a normal approximation to the binomial distribution, which is what we're asked to do in the last question, number 4. Let's redo problem number 2, but using the normal approximation. Now, in order to do that, we do have to figure out the mean and the standard deviation for the normal distribution. And we did that using the formulas for binomial distributions given here. And so we have our mean and our standard deviation, which I've indicated in the picture here. And we're just trying to find the area to the left of 300. So we're pretty good at these calculations at this point. We calculate a z-score first. And you'll see that that value of 300 is 2.34 standard deviations below the mean. And we then take that to table A in order to find our area, which is about 1% at 0.0095. And we can even compare that back to the answer we got with the binomial distribution. And sure enough, those answers are fairly close. So this concludes the video for binomial distributions day 3. Thanks for watching.